Chapter 15, we're going to talk about some more K, so KSP and KF. KSP is the solubility product. KF is the formation constant. And we'll add these to our ever-growing sort of list of Ks. So let's start with solubility equilibrium. Solubility equilibrium are equilibrium constants for things that are typically insoluble. So KSP is the solubility constant, our products. And it really is, as we will see, for things that are typically based on those solubility rules, which we all remember. Yes, some nitrate soluble and everything, group 1 soluble and everything. That's all I remember, but there's the rest of them on there as well. So most of the KSP sort of expressions are written like a normal equilibrium constant expression, which is our products over reactants. The only difference is on most of these equations, you will always have, for the most part, a solid over here on the left-hand side of the arrow. That means for the most part, when you write these KSP expressions, they are essentially just the products, which are our ions. And that is typically how these guys go: solid on the left, ions on the right. And that's sort of how this equilibrium sets up. Now, something like sodium chloride, you may be familiar with from your solubility rules. Chlorides, iodides, and bromides are soluble in everything except for silver, lead 2, and mercury 1. In this case, this is silver, which means it's insoluble. So we could write a KSP expression as the concentration of our silver ions times concentration of our chloride ions. And that is what is known as the KSP. Now, we do it just like we do any other equilibrium expression. So if you happen to have something that breaks apart into, like we see on the second one, a couple of fluorides, you do need to, like normal, take that into account when you write your expressions. So R2 for R2 like normal, R2 over here for R2, and R3 and R2 needs to be taken, obviously, into account. Now, when we think about solubility rules and we think about things being insoluble, we oftentimes think of them as sort of a hard rule that if the solubility rules say it is insoluble, no matter what the situation, when we put those guys together, we will get a solid that will form. And the truth is that's not always the case. So there's a lot of factors that affect solubility that we're going to talk about in this chapter. Some of it is pH, some of it is concentration of the ions, some of it is the presence of other ions that may be there as well. So anything, even from your solubility rules that say it is insoluble, everything has some degree of solubility. So even something that is technically insoluble based on solubility rules, there is some degree of it that will basically be soluble. It may be a very, very small amount, super small amount, but there's some of it that will break apart. So that's why something like what we see here with silver chloride, although from the solubility rules, we consider it to be a solid, in actual solution, there is a little bit of silver ions floating around and a little bit of chloride ions floating around. But the vast majority of it is still silver chloride, still together in its sort of solid form. We could also look at another letter that we've seen before, which is Q. And we could use Q with KSP to help us decide whether or not a precipitate will be made. A reminder that Q is the reaction quotient and Q is calculated the same as K, which means if I were to write the Q for this guy, it would be the exact same thing. So we used Q right before to determine whether or not if we were at equilibrium, and if we weren't at equilibrium, which way we need to go to reach equilibrium. We could also use Q and compare it to the KSP to help us decide if a precipitate would form. If Q is less than the KSP, we have an unsaturated solution. Unsaturated solution means if you add more solid, it will dissolve, basically, right? We haven't hit the maximum amount of solute, right, that will dissolve in that solvent at that temperature. That's what an unsaturated solution means. And we would expect no precipitate to form. So if you think about how these equations are always sort of written, solid to liquid, and if you do split it up like this, Q is less than K, it will point to the opposite side. I guess liquid is a bad word there. Aqueous be the better word. It goes opposite of where it points, so it should be aqueous ions in that case. If you calculate Q and it's equal to the KSP, that is a saturated solution. Saturated solution is pretty much the point where you've hit the maximum amount of solute that will dissolve in a given amount of solvent. And basically it will all dissolve, but if you put just a hair more, then you will not get any more of it to dissolve in there. And that happens when we calculate the Q and it is greater than the KSP. So if Q is greater than the KSP, going the opposite way, we would expect a precipitate to form, and you have a supersaturated solution. A supersaturated solution is a solution where you have way too much solute dissolved in a solvent at a given temperature, and basically it all comes out of solution and you make a solid that would form. Any questions on that there? God. So here's a table from your book of all the KSP values, which you'll memorize. No, I'm just kidding. But what we do see when we look through these that you could clearly not see very good on this is that pretty much all the KSP values are really small. Yeah. So for example, that's like to the minus 45, you know, minus 20-ish or so, minus 30-ish. So those are very, very small values of K. That means that when I reach equilibrium with these really small values of K, would I mainly have reactants or products? Small value of K would mean you would have reactants, which means for the most part, that's what you have, right? Is you have solids, which is always on the reactant side. But again, a little bit of it is going to come out into solution. So that's why we consider these things still to be insoluble, because a majority of it is going to stay together and really not break apart. But again, even things that are insoluble will still have some level of solubility. More KSP. So there's typically two types of things that we are looking for when we're doing these type of problems. One is the molar solubility, and that basically is I guess a fancy way of saying molarity. So that is basically the molarity of that solution. So the molar solubility is the moles per liter, the moles of solute that will dissolve in 1 liter of a saturated solution. Molar solubility, when we do sort of tables and stuff like that, is oftentimes represented by the letter S. So if you see S, S typically stands for molar solubility. The other solubility is just regular solubility here in grams per liter. That's how many grams are dissolved in 1 liter solution. If I have molar solubility and I want to go between molar solubility and grams per liter, what is the thing that allows me to go between those two? So what allows me to go between these two? Basically, the only thing I'm changing is grams per mole, moles to grams. That is the molar mass. Yeah. Not everybody at once. It scares me. All right. So the molar mass, yes, from the periodic table is the guy that allows you to go between those two. Yeah. All right. So there's two types of problems. One type of problem is you're actually asked to calculate the KSP for the compound. So to do that, you would want the solubility of the compound you want the molar solubility or moles per liter of each of the ions that are present. And then you could actually put it into the KSP sort of expression. When you do that type of calculation, when you're asked to calculate the KSP, you don't necessarily have to do an ice table. You can, but you don't have to do it. Now, the other one does require you to do an ice table, and that is if you're given just the KSP and you want to know the solubility of the compound, either the molar solubility or the solubility in grams per liter, or any other unit of solubility, I suppose you want, that does require you to do an ice table. So really the bottom row there does require an ice table. The top one, you could do one. It's sometimes helpful to make sure you don't screw up the calculation. But if you understand molarity and how it works with ions, you don't necessarily have to do it. So let's take a look at one here just to show you how it works. We will do it here together. So in this particular case, the solubility of silver phosphate, not sure why there's the exaggerated spaces for dramatic purposes. Silver phosphate at 25 degrees is 1.6 times 10 to the minus 5 molar, basically. What is the KSP? So in this particular case, we're looking at for the KSP. So we definitely know that this guy is a solid. So we can set up sort of our equation, and that would be this. This will break apart into 3 silvers and a phosphate in this case. Now, we can do an ice table here. By taking our knowledge maybe of how things break apart, but we will kind of do this. We could start with we could start with 0 and 0 to show you how this ice table will normally look. So normally we start with zeros of those. The change here would be plus 3s and plus s in this case. Once again, the S here stands for the molar solubility. Which again is the molarity. We're going to come to equilibrium here. And as you can see, we still take our coefficients into account, 3s and s. Any questions on sort of that ice table? So at this point, just like normal, we would go into our K expression, which in this case would be the KSP is equal to the concentration of silver. And we do need a cubit times the concentration of phosphate. And if this was a case where we did have the KSP given to us, we would equal it to the KSP value given to us and then solve for S and all that good stuff. But in this particular case, we do not have the KSP given to us. We're looking for the KSP. So we could very much now use this number right here, which is the S. Yeah, that is the molar solubility. Which means if I put my equilibrium into here, that is 3s cubed times s, which means I should take 3 times 1.6 times 10 to the minus 5 and cube it times 1.6 times 10 to the minus 5 as well. Any questions on that there? All right, so if I do this hopefully correctly, let's try it. We're going to take 3 times 1.6 to the minus 5. I am then going to cube it. Going to times it by 1.6, exponent button -5. Going to give us a, I think it says 1.8 to the minus 18 as the KSP value. Any questions on that one there? Now, I did an ice table here just to show you sort of how the ice table would look if you don't want to do an ice table for this particular one. You did not need to do that if you understand molarity works, right? So once again, this guy is going to break apart into my 3 silvers and my phosphate. And if the molarity of this guy was 1.6 times 10 to the minus 5 molar, it is a 1 to 3 relationship, which means you take 3 times 1.6 times 10 to the minus 5. It is a 1 to 1 relationship, which means the molarity of this guy is 1.6 times 10 to the minus 5. And then you could just take them into here. That is essentially what this did for you. By doing the ice table is multiply it by 3, multiply it by 1, and you hopefully wouldn't have screwed up. But if you understood that, you could have just got the concentrations of each of the ions and went into the KSP expression and solved for the KSP without necessarily having to do the ice table in this particular case. I might recommend the ice table because frankly, people get under this impression when they do these type of problems of I'm multiplied by 3. Do I still need to cube it, or I'm cubing it? Do I still need to multiply it by 3? So you get into that internal conversation with yourself, which is a bad conversation. Don't have it with yourself. Yes, but that's very common. So if you do the ice table, even in a situation like this where you don't need to do it, it will still maybe visually show you that you need to still multiply by 3 and still need to cube it and stuff like that. But again, you could just use the molarity relationship and go into the KSP expression. They both should obviously give you the same answer. Any questions on any of that there? All right. I did one. Now you do one. What is the solubility of silver chloride in grams per liter? I'll give you silver off the periodic table. There is something. What is that? Like 107.9 still, I think. I hope. Chlorine is 35.45. All right, take a couple minutes there and see what you come up with. KSP for silver chloride, 1.6 times 10 to the much your solid on the left, ions on the right here. And again, our KSP is above there. So since all we are given is KSP in this case, we will start initially with 0 and 0. Our change here, once again, will be plus S and plus S. That means at equilibrium here, we have S and S. Any questions so far? Now, we didn't do anything, obviously, with this guy because he is a solid, right? So he's not going to be in anything. So we don't want to put anything there. The KSP expression in this case would be our products, which is the silver concentration times the chloride concentration. And that would equal our KSP there that I got away from. There it is. 1.6 times 10 to the minus 10. Just like a normal ice table, we will then take our equilibrium line and put it into our expression. That will get us S squared is equal to 1.6 times 10 to the minus 10. Taking the square root there. Gets us an S value of 1.3 times 10 to the 1, 2, 3, 4, 5 minus 5. And this S is the molar solubility, which is really the molarity here. First off, any questions on that there? Now, that S is the concentration of silver at equilibrium. It is also the concentration of our chloride at equilibrium. And is that a lot? Not a heck of a lot, right? I mean, that's, relatively small. So at this point here, we want to know what is the solubility of silver chloride. This S that you get here is the same solubility of the whole thing, because if you go backwards, it's a 1-to-1 going backwards, right, from the silver, or 1-to-1 going backwards from a chloride. So that would also be the moles per liter of silver chloride. which if we use the molar mass of silver chloride, which is 107.9 plus 3545, gets us 143.4 grams times 1.3 to the minus 5 gives us a solubility of silver chloride of 0.0019 grams per liter. Is that a lot of silver chloride dissolved in 1,000 milliliters? It is a very small amount, right? So basically this says that you could take 0.002 grams of it and 1,000 milliliters, and that's as much as you're going to get to dissolve, which is not a very much, which is why we consider silver chloride to be insoluble, right? Basically. So even under kind of normal conditions here, you're not getting a lot of it to actually dissolve, but it still is something that will basically be soluble, even though it's technically insoluble. Any questions on any of that there? All right. So why don't you try this one here? What is the concentration of aluminum 3 in aluminum hydroxide? I don't know why the 3 went so far over. Yeah, everything shifted apparently. All right, KSP for that is 2 times 10 to the minus 32nd. Okay, let's take a look at this one here. So once again, we're just given really the KSP, which is very common in these type of problems. So we will start with our equation. Once again, we see a KSP value for this guy, so we know it will be solid. This will break apart into aluminum and 3 hydroxides in this case. Initially here, we're going to have 0 and 0. Change will be plus S. And again, we do want to make sure we do take into account the 3 there. So it's going to be plus 3S. We're going to end up here at equilibrium with S and 3S in this case. We're going to go into our KSP expression, which will be the concentration of aluminum times the concentration of hydroxide. And once again, we do need to still cube it there as well. Bless you. Putting in our values here gives us S times 3S cubed will equal 2 times 10 to the minus 32. Any questions so far? All right, doing some math here. That gets us 27 S to the 4th is equal to 2 times 10 to the minus 32. Remember, you got to cube the S and the number. People always never do the number. Yeah, so that is 3 times 3 times 3. Yes, gives you 27. Again, it's a very common mistake. People just do the letter, not the number on that. We're then going to divide the 23 to the other side and also take the 4th root of it, I believe. So that's going to be 2 to the minus 32 divided by 27. Gets us S to the 4th equals 7.41 times 10 to the minus 34. That is the 4th root. Yeah, to both sides. We're going to end up with something. There we go. Something like 5.2 times 10 to the minus 9 molar. If you have a calculator, it may just be all zeros and a 5 at the end if you ran out of room. Yeah, you're not in scientific notation. By the way, to do the 4th root on your calculator, caret 1 divided by 4. Yes, basically we'll do that for you. Want the square root 1 divided by 2, cubed root 1 divided by 3. In case you don't have a dedicated button, that is what you do. Yeah. So on your calculator, you should have a caret button, parentheses 1 divided by whatever root you want to do. We'll do that for you on your calculator. Yeah. Any questions on that there? That obviously would be our concentration of aluminum, as our table shows that the aluminum does equal S. What happens if I wanted the concentration of my hydroxide? What would it be? Yeah, so since the hydroxide equilibrium is 3 times S, we would take 3 times the 5.2 times 10 to the minus 9. And that would get us something like 1.6 times 10 to the minus 8, or 2 if we rounded with the sig figs there. Why might that be important? That would allow you to figure out what about this solution. You know the OH minus, you can figure out the pH, yeah. Where you get the POH, then you get to the pH. So you can figure out what the pH of the solution would be as well, yeah. Any questions on any of that calculation there? All right. So let's talk about actually using KSP values to help us determine which one is more soluble, which one is less soluble. And you can do that in a certain situation, and in other situations, you should not use the KSP values to compare. So let's talk about when we do have salts that basically produce the same number of ions. So we have a list here of silver iodide, which will produce silver and iodide. That is 2 ions. We have copper 1 iodide producing copper and iodide. That again is 2 ions here. And obviously our calcium sulfate, when it breaks apart, calcium ion and a sulfate ion, which is 2. So in a situation, if you are comparing 2 salts that basically break apart into the same number of ions, what that basically means, if you roll through the ice table, you're going to end up with the same sort of result calculation. You can use the KSP values directly to determine which one would be more soluble and which one would be less soluble. So if we are doing that, if my KSP is larger in one of them versus the other, the one where the KSP value is larger, is it more or less soluble? So again, if you're comparing 2 salts where the KSP value of one of them is larger, is it more or less soluble? Well, let's think about it. In the KSP arena, product side is aqueous, reactive side is solid. And if I have a larger KSP, well, that would mean I would be more reactants or products. Products are aqueous, which means it would be more soluble. Yeah. If you had a KSP you're comparing that is less than the other guy, that would mean that you would have more reactants, right? And it would have solid and it would be less soluble. So if you are going to use the KSP values to help you decide between 2, you could definitely do it as long as they do break apart into the same number of ions. And again, the one with the larger KSP value should be more soluble. The one with the lower KSP value should be less soluble. That's important in case in a situation where you want to take out one ion versus the other. So, you know, the one ion is going to be less soluble. You could take it out first and then leave the other one still floating around. It is what we'll talk about here in this chapter, selective precipitation. Just take one thing out at a time, basically, leave everybody else floating around. So in this case, if you did look up the KSP values, we would see that the larger KSP value is for our calcium sulfate. Our lowest would be for our silver iodide. So the silver iodide would be the least soluble of those all. So it would probably come out perhaps the solution last in that particular case. Now, if you do not have salts where they break apart into the same number of ions, you cannot use the KSP values to help you compare. You've got to do the calculation like we just did. So you got to kind of do the calculation and figure out the molar solubility. So for example, if we look at this one, which is copper 2 sulfide, that is 2 ions. That is silver sulfide, which is 3 ions. And that is bismuth, a lot of ions there. We'll go with 5. And in this case, they do not break apart into the same number of ions. If we went solely based off of KSP to help us determine solubility, what we would see is the larger KSP is this guy, which would tell us that this guy would be more soluble. And this is the smaller KSP. This guy would be less soluble. But when you actually do the calculation, what you actually see is the opposite. When you do the calculation, it is actually this guy that is the most soluble. And it is actually this guy up on top that is the least soluble. So you cannot use the KSP values in a situation where you're comparing things that make multiple or different numbers of ions. You got to literally go do the calculation like we just did and compare them at that point. Any questions on that? But again, if they are sort of a same number of ions in each, you can use the KSP value to help you decide. Any questions on that there? All right, so let's talk about some things that definitely do affect the solubility of a solution or a product. And the first one is the common ion effect. So the common ion effect is what we saw with buffers. And much like what we see with buffers, when you have a common ion, it decreases the acids dissociation or the base dissociation. The same thing happens here, and it's a very simple idea to visualize. Once again, if you just think about these reactions where we have solid on the left, aqueous ions on the right, if I have a common ion, which side would it has to be on? It would be like adding to the right-hand side, right? And our Le Chatelier's principle would say it would then shift to the left, right? Which means more solid. So when you have a common ion present in this situation, it basically will decrease the solubility of that salt. It will keep it together based on Le Chatelier's principle. And we do see that the solubility will go down based on or versus just water by itself. So for example, if we look at silver bromide, where this is the KSP for silver bromide. And if we did the solubility of silver bromide in water, we would do our ice table. Initially, again, 0, 0, change plus S at equilibrium, S and S. So this would be just in water. Okay. And here, this would go into our KSP, which would be our silver times our bromide. And that would give us S squared is equal to 7.7 times 10 to the minus 13. Taking the square root there will give us a molar solubility for silver bromide of we'll call it 8.8 times 10 minus 7, I believe there. So that would be the molar solubility of silver bromide in water, which for reference sake is approximately, we take that and times it by 187.8 grams per mole, which is the molar mass. Roughly 0.000165 grams per liter. Is that a lot? That is not a lot, right? So that's a really small amount that's basically dissolving under normal conditions of water. And again, why we consider it to be insoluble. But now if we put that same silver bromide into a solution of not just water, but that does contain 0.001 molar sodium bromide. Sodium bromide is a salt that will not set up in equilibrium. It is soluble. It is going to break apart into sodium and bromide. The common ion here is the bromide, right? And if we know the concentration of this guy is 0.001 molar, the concentration of the bromide in this case would be the exact same thing, as it's a 1-to-1 relationship. So how this affects us when we do our calculation for the solubility of silver bromide, we'll once again do our ice table here. And initially this would be 0, but initially here we will have some bromide being contributed by the sodium bromide in that solution, so it won't be 0. The rest of it will look very similar. This will be plus S and plus S, which means at equilibrium S and 0.001 plus S. Any questions on that so far? Just like before, that's going to go into our KSP expression of our silver and our bromide. And that will give us S times 0.001 plus S is going to equal 7.7 times 10 to the minus 13. I would highly say that the KSP value is large or small. Whenever we have a small K value and we're doing these type of calculations, we could assume what? Yeah, same idea as we assume X is equal to 0 here. The change here is going to be really small, right? Even smaller because we have a common ion happening here. So we could safely assume here that S is equal to 0 because of that. Obviously not all the S's, so it would just be the S we're plussing here. So it would just be that S. So that would get us, I'll come up here, that would get us S times 0.001, and that will equal 7.7 times 10 to the minus 13. Once again, here we're then going to take 7.7 to the minus 13 divided by 0.001, going to get us a molar solubility of 7.7 times 10 to the minus 10 molar. And just to keep us on track with the same sort of numbers, if we want the other solubility there, using the molar mass, gets us 0.12345 grams per liter. And which one is it more soluble? Is more soluble in water, yeah? In water, you can at least get 0.0002 grams in. With the common ion there, pushing it back the other way, you could only get 0.000001 grams, which is a lot less, yes? So we do see the effect of the common ion is going to keep that guy together, not going to allow it to break apart anymore, and the solubility does go down. Any questions on that there? So one important effect on solubility is the presence of a common ion, which obviously will decrease the solubility of it. Let's take a look at one here. So why don't you try this one here? The KSP of silver chromate is 9 times 10 to the minus 12. What would be the solubility if it was in a solution of 0.1 molar potassium chromate? By the way, I checked my assumption in my head and it was good, but it probably will be good in most cases. If you do check your assumption like normal, take our XS value divided by 0.01 it was in that case, it will come out okay as well. Usually they'll come out okay with KSP problems because the K values are super small to begin with, yeah. So usually it's okay to make that assumption. All right, give it a go here. For chromates, and that tells us that's really the one that's going to set up the equilibrium here. So that's what we'll start with. We got a little silver chromate action. Since I see a KSP, I'm confident that's going to probably be solid. That should break apart into a couple of silvers and like a little chromate action happening. Here. Yeah, that's what it says. All right. So we also though have some potassium chromate that we're going to put this into basically. And again, potassium chromate here would be a little K2CrO4. Since that is potassium, that means that's going to be soluble and that will not set up an equilibrium, but will completely break apart into a potassium, probably a couple of potassiums, and a chromate here, ions. Once again, looking at the concentration of our potassium chromate, which is 0.1 molar, it is a 1-to-1 relationship between those two. I'm sorry, I got like really bad glare. Or is it there? That's better. Which means that this would be 0.1 molar here. We didn't need it in this problem, but the concentration of potassium would be. It would be 2 times 0.1 molar, right? Which would be 0.2 molar. And just to remind you how that works, but it is this guy that is obviously our common ion in this case. So initially here, the importance of that, much like when you do an ice table for a buffer, you got to have somebody on the right-hand side or it's no longer a common ion type situation. So we will have 0 and we will have our 0.1. Change here going to be plus 2s. Once again, because of the coefficient, we got to make sure we do that. And plus s. That means that when we get down there, we got 2s and 0.1 plus s. Any questions on the ice table or anything like that? At this point, we could do a little KSP expression, which would be our silver concentration also being squared because of the 2, and our chromate here. Putting in our values gives us 2s squared times 0.1 plus s is equal to the 9 times 10 to the minus 12. Once again, this is a small value of k, so we could assume s is equal to 0. And once again, it is going to be just the s there that we were going to add. You can't get rid of everybody. Otherwise, logically, you have nobody to solve for. That gives me, if I'm doing my math right here, 4s squared times 0.1 is equal to 9 times 10 to the minus 12. So however you want to do that, I'm going to take 4 times 0.1. And then I'm going to take 9 to the minus 12 and divide it by that. I feel like maybe I did it right. Going to give me s squared is equal to 2.25 times 10 to the minus 11. At this point, a little square root action on both sides. You're going to get me too many zeros. 4.7 times 10 to the 1, 2, 3, 4, 5, 6 molar here. That once again would be the molar solubility for our silver chromate. In this particular case, if we wanted the concentration of our chromate at equilibrium, what would it be? It would be 0.1 plus that number, right? And if we wanted our concentration of just the silver ions, we would have to take that number and multiply it by 2. But that number is the solubility, though, of the silver chloride. If you just look at the silver part, it's a 1 to 2 going backwards. So you divide out the 2 and it comes back to this number at the end. So ultimately, when you do solve for that S, that really is the solubility, the molar solubility of the compound. And then sometimes you want the ions. If it's not a 1-to-1, it breaks apart into, you do have to do obviously some calculation to get those guys' concentrations. Any questions on that there? So again, this is one important thing that does affect the solubility of something as to whether or not you will see a solid or might not see a solid. Another really important effect of solubility, or that can have an important effect on solubility, is the pH of the solution. So the pH plays a really important role in the solubility of things. We don't do that experiment at all anymore. They got rid of it, but years ago, we used to do experiment here, and a lot of places they do experiments, which are known as qualitative analysis. And in qualitative analysis, pretty much all you do is experiments where you are trying to selectively precipitate out ions in a solution one at a time, basically, or sometimes more than one at a time. But you're basically taking ions out of solution in a very organized manner. And a lot of those steps, when you do those things, requires you to adjust the pH to a certain level, make it acidic, make it basic, and all that helps keep certain things in solution and allow other things to sort of come out of solution as solids. So pH plays a really big role in the solubility of things. So as we just saw, the presence of that common ion will decrease the solubility. If you have an insoluble base, can be dissolved in acidic solutions, and vice versa. If you have an insoluble acid, a base basically can dissolve that for you. So if we look at this guy right here, which is magnesium hydroxide, and the KSP here for magnesium hydroxide is 1.2 times 10 to the minus 11. We could do a quick calculation here, like we've been doing with our ice table, and take our magnesium hydroxide to magnesium plus a couple of hydroxides. And again here, this would be 0 and 0. This would be plus S plus 2S in this case. And at equilibrium, we would have S and 2S. Putting this into our KSP expression, which is right here, will give us S times 2S squared is equal to 1.2 times 10 to the minus 11. That is 4S squared, 4S cubed, I hope. Yes, 1.2 times 10 to the minus 11. Dividing the 4 to the other side, 1.2 to the minus 11 divided by 4 gives us S cubed is equal to 3 times 10 to the minus 12. Taking the cubed root here, again, you could go caret parentheses 1 divided by 3. Gives us an S value of 0.000144. Now, that S value can be very helpful for us when we're talking about pH, as we talked about earlier. If we go back to our ice table, we see that 2S is the concentration of hydroxide at equilibrium. So if we get the concentration of hydroxide here, which would be 2 times S, 2 times our S value we just calculated there, 0.000144, will give us a concentration of 0.000288 molar. That will give us a pOH of, we'll call it 354. And that would then give us a pH of 14 minus 3.54. There is something at the end of my calculation here, I think. So that is a pH of 10.46. That pH represents the pH of that solution. Yeah. So if you took that solution, you made a magnesium hydroxide type situation, it would have basically a baseline pH of 10.46. It's acidic or basic? It is basic, which is good because it's magnesium hydroxide, it's a base, right? So this is definitely a basic pH. All right. So you decide, well, I don't got a lot of it dissolved there at 10.46. I would like to decrease the pH below 10.46. What will happen to the solubility of this as I bring the pH below 10.46? Will solubility increase or decrease? Well, let's take a look at the equation here. In order for me to drop the pH below 10.46, would I have to add an acid or a base to do so? It has to add an acid, right? And when I add an acid, I am essentially adding what? What is an acid? It's something that produces hydronium or H plus, basically, right? So I'm basically adding H plus. Thinking about it in terms of Le Chatelier's principle, when I add H plus to this equilibrium, what's going to happen? It is going to take away the products because there is no H plus in there, but there is OH minus. And what's going to happen is these two guys, right, when they come together, is going to make water, right? Which, as you correctly said, basically will remove products. And Le Chatelier's principle would tell us the equilibrium should shift which way? Should shift towards where we removed it. And towards where we removed it, right, is aqueous ions, right? These are aqueous. So that is going to increase the solubility of this. Yeah. You'll get more of it to start to dissolve, basically, in this case. And that's what it means when we have an insoluble base is soluble in an acid. As you add acid, you're removing the hydroxide. When you remove the hydroxide, it's going to allow more of it to break apart to produce hydroxide. Yeah. Any questions on that there? Yeah. Do you have to square the two? Which one now? In order to get the concentration of hydroxide. Yeah. You don't, because that would be just this right here. Yeah. Because that would be technically the OH minus at equilibrium would be that number on the bottom there. Yeah. Okay. Well, that's good. Otherwise, there's like a lot to erase, and we're kind of at the end. I'm just gonna go and look at it. No, I think it should be good. But yeah, it would just be that 2S at the bottom, which give us the equilibrium concentration of the hydroxide at that point. So let's talk about here to finish up, what would happen if we kind of did the opposite here and we decided to increase the pH above our 10.46 cutoff. So to increase the pH above our 10.46 cutoff, we would have to add a base, right? And adding base basically is adding hydroxide, right? So we'll use this guy up here. Looking at our equation, if we are going to add hydroxide, Le Chatelier's principle will tell us we are essentially now doing what? Adding more hydroxide, which means the equilibrium should shift which way in this case? Should shift to the left, which means that is more solids going to form. So if you brought the pH above 10.46 in this case, we would actually see the solubility decrease. We would actually be making more solid at this point. So that's why it's important in a calculation like this, where you have an insoluble base or acid, you could actually calculate the pH and you know kind of your cutoff of that's the pH where, you know, pretty much I got a solid. If I take it above that, in this case, we'll have more solid. If I take it below that, I will have less solid. When we take it less than 10.46, even if I take it to like a pH of 8, which is still basic, is going to be more soluble than it was originally because you dropped the pH a lot there. So you don't have to take it all the way to an acidic pH to get more of it to dissolve. You just have to lower it lower than its baseline pH. Any questions on that there?